Thank you, Jane, for a very generous introduction. It's my pleasure to be back. I've been here a few times, and every time I come back, I have more friends to meet, colleagues, collaborators. So it's great. It's great to visit our eastern neighbor here in Riverside. Since it's a colloquium, I try to structure my talk around the basic general ideas. So I just want to convey a few exciting ideas. Some of them are a bit abstract. Some of them are directly related to experiments. I'll give you a flavor of a few things we're thinking about, proposing to experimentalists. Spin hydrodynamics and insulators is an umbrella term that may not really mean anything by itself, but as we progress through this talk, hopefully you'll get a bit of an idea of what we're thinking about. But the key here is not so much the spin. The key here is hydrodynamics in insulators. Okay, so I'll try to start at a very, very high level, maybe kind of useless in some sense, too general. But I'll try to sort of step back and start discussing transport phenomena in solid state in general. Okay, how do we think of transport phenomena? Starting, of course, with electrical currents, heat currents, sort of conventional transport, and then progressing via this important intermediate step that somehow connects really a very, very old-fashioned transport, like diffusive type of transport behavior, to the topic that I'm really pitching at in this talk. So I'll step through this kind of historical development of transport in solid state. I will use the term hydrodynamics in the broadest sense, as some kind of coarse-grained flow of a conserved quantity, but in a solid state, specifically in a solid state environment. There will be three illustrative cases, and really my talk will be mostly the new aspects. To most people, what will be the new aspects will have to do with these three examples that I will step through. And by these three examples, I think I will really illustrate my point. So they have to do with some winding dynamics, skyrmionic dynamics, and this is the newest idea that we're really excited about. Again, very, in some sense, very old material, but novel type of dynamical transport phenomena that we're starting to think about. Okay, so like I said, okay, let's take a step back. Historically, when you think of transport in solid state, the first thing that comes to mind is some kind of particle motion, like electrons are moving, like in a Sommerfeld theory of transport conductivity of metals. Phonons don't have to be elementary particles, could be some quasi-particles like phonons or magnons moving around, and at the simplest level, there's quite a bit of scattering in solid state, so that motion would be diffusive, at least as a starting point of thinking. So you would imagine fluxes associated with this transport to be somehow proportional to gradients of some local, meaningful, measurable quantities, such as densities, like particle density. And then as we progressed throughout 20th century, we started coming across more exotic transport phenomena, like superfluidity, superconductivity, in which the transport is collective and cannot be easily broken down into motion of individual particles. So that would be, I guess, superfluidity, superconductivity. That's a quintessential example of that, in which the flux is given by the gradient of, let's say, phase of some order parameter. So that's a little bit more abstract and more difficult to grasp intuitively, and that's why superconductivity is still somehow such an somewhat enigmatic and somewhat mysterious phenomenon, at least when you start learning about it. Now, the aspect of the superconductivity that is key for this talk is its topological stability. And understanding that will bring us to the notions of spin superfluidity, and then more generally topological hydrodynamics, of which superfluidity, superconductivity is just one special example. Okay, so that is the outlook for the progression of my talk. Via spin superfluidity, I'll try to formulate our general perspective on topological hydrodynamics in magnetic insulators. And much of what I'm going to say concerns, in many real materials, concerns even room temperature transport phenomena. So we don't have to go to like very low temperature regimes. All right. So these are the cartoons of this progression in the field of spintronics concerning transport in insulators. When some years ago, maybe 5 to 10 years ago, so we started thinking of transport in magnetic insulators, spin transport, in terms of motion of magnets, which carry spin diffusively relative to some order parameter. And then a few years ago, we shifted our attention to to the idea of spin superfluidity. I'll explain what I mean by that. And now the most recent thing is this, and that's really the topic of this talk. Okay. All right. So, like I said, the starting point of thinking of some kind of hydrodynamics will be understanding the appropriate conservation law. All right. In the really old-fashioned kinds of hydrodynamics, that conservation law has to do with just a simple counting of particles. Different, of course, regimes of transport. There's some gas, liquid, even theory of elasticity. In my broader sense, I will think of it as some kind of hydrodynamic phenomenon in which particles fluctuate around, even though they may not move far away, but there's still a conserved quantity that fluctuates around. So the conservation law here is just the number conservation of particles that you can count one by one. In the topological hydrodynamics that I will formulate in this talk, instead we're counting objects which are by nature delocalized. So they're not point-like objects. Instead, we're counting some kind of topological twists in a system. So an illustration of that is shown here. So it's some XY magnet with some one-dimensional magnetic texture with order parameter line in plane, and it twists. So let's say it prefers to lie along the x-axis. It has an isotropy to point to the right or to the left. And then the elementary excitations are the domain walls, and each domain wall is chiral. So it has a clockwise twist or counterclockwise twist. So we can assign a topological charge to it. Let's say the angle of twisting divided by pi. So there's charge plus 1/2, here charge minus 1/2. And the key is that so long as we restrict our attention to low energy dynamics, magnetization allowed to fluctuate only within the plane, the total winding number is conserved. The total winding is conserved, and we can define the density of this winding number, simply the gradient of the phase. The total winding is conserved, but of course it can shuffle from one part of the system to another, so we can develop a hydrodynamic description of that shuffling. Okay? So again, this is again just rephrasing for the people familiar with superfluidity. This is also how you could think of superfluidity in one dimension, and the stability, topological stability of superfluidity that has to do with the conservation of such twists. All right, so that's the first step, and then of course later on we'll try to make contacts. So that would be some kind of like a medium for this dynamics, but whenever I understand the medium, then I'll try to apply some contacts and try to measure some kind of transport behavior as a property of some device or a circuit. Okay. So the motivation for our work is not entirely abstract. In fact, the motivation, our interest slowly over the few years developed based on the experimental progress, on the development of the tools that allow to inject such transport, topological transport signals into insulators. For the experts here, there are quite a few experts. I'm implying here things like spin torque, spin Hall effect, spin Seebeck effect. So there is a set of relatively new phenomena that became tools just over the past few years that allow us to put some contacts, metallic contacts, on an insulating medium, and could be very generic insulating medium, and try to drive some neutral flows, such as flows of spin. But I will generalize this notion to flows of some topological textures, starting with spin and then going towards more general topological textures. So that basically gives us a sort of twofold, opens twofold agenda. One, we can use now this transport, first of all, understand, but then we use this transport probes as a basic tool to study quantum materials and heterostructures. And turning the tables around, we will ultimately utilize this new transport phenomena to think of new devices and maybe even computing architectures. I'm not going to go as far as discussing computing architectures here, but I will give you some sort of hint of devices, not really in some useful sense, but just as a conceptual devices. Okay. So again, like I said, think of hydrodynamics in the broadest sense possible. So I could illustrate all the relevant key elements by considering some kind of plumbing setup. We have a conserved quantity that can slosh around. Now I'll put this conserved quantity in a circuit. So this is my circuit, which is connected to reservoirs. The reservoirs are containers of my conserved quantity that I can bias quasi-statically. For example, here by gravitation. In some magnetic system, I could apply static magnetic field, to kind of raise the effective, some kind of effective chemical potential of one region versus the other. I also have dynamic active elements, which could, through which I could channel energy into my system. So this would be like a pump, and that pump could even, push flow even against the gravity. Or against some kind of natural quasi-static bias, and I could realize such pumps by various modes of magnetic dynamics. And I could think of some nonlinear elements like valves here that, in my case, could be realized through some localized magnetic solitons. So, in principle, even though I'm not going to somehow break it down in full detail, in principle, just to have some rough idea in mind, so we're thinking in these terms, and we do have ideas for these different ingredients: pumps, nonlinear elements like valves, transistors, and reservoirs that we can bias. Okay, so that's sort of the rough picture to keep in mind. All right. Now, again, let's take a step back and remind. Okay, what are the most common hydrodynamic transport phenomena that are out there in solid state? Well, electrical current and the heat currents are the two most common generic hydrodynamic phenomena. In fact, heat flow is the most generic because it goes pretty much from anywhere to anywhere. There are always some excitations which carry heat. Electrical current is a little bit more specialized, and in some sense, that's why it's really so useful. And we have circuits like this with batteries, switches, some kind of useful device. The moment you have, first of all, just a side remark, any conserved, the hydrodynamics of conserved quantities should be understood if they're present in your system, because they're typically important just for basic understanding of flow energy physics. But apart from that, okay, coming from some kind of functional point of view, we can use this hydrodynamic phenomena to do something useful. I will take for granted that electrical currents are useful. Okay. Now, the moment two of such flows are present, or more than one flow is present, we can couple them. The simplest case, which is couple them by drag. Each of the if you apply electrical current here, it also drags some heat flux and vice versa, and that's the basis for thermoelectric phenomena, such as power generation using the Seebeck, ordinary Seebeck effect, in which applying a heat current drags charges. For example, in this thermocouple, if you put two wires, n-doped, two semiconducting wires, n-doped and p-doped next to each other, you could easily generate voltage in this circuit by dragging the positive and negative quasi-particles down by the heat flux. So the moment two fluxes are present and one of them, at least one of them, is directly detectable, we can use this flux, this hydrodynamic phenomenon, to study this hydrodynamic phenomenon. Okay, and that's kind of going to be the spirit of how, in the end of the day, once I formulate some, let's say, somewhat more exotic hydrodynamic effect, how I'm going to connect it to the experiment. I'm basically going to couple my more abstract hydrodynamic effect to either this or that. And again, for the experts here, this would go under the designation of spin Hall and spin torque effects, and this would go under the designation of spin Seebeck effect. So that's going to be my connection to the directly measurable reality using tools which are already available in the lab. So I don't have to envision some kind of unusual experimental tools. All right, and in this talk, I will focus primarily on the electrical currents. I will say little about heat flows and using heat flows to couple to topological hydrodynamics. But just as a side remark, that has become also a big subfield in spintronics and also very interesting. Just in the interest of time, I will leave it out for most part. Okay. So two examples, and I'll have one more example, the spin glasses. I'll get to that in the very end. So the two examples which are easy to illustrate and which have become quite important recently. One is spin superfluidity in 1D. I will form this theory is formulated as I already alluded to in terms of texture and in terms of topological stability of the winding number. So winding number is probably the simplest topological invariant out there in physics, so we start there. The second example that is just a little bit more complex, but pretty much just as simple, is skyrmion dynamics in 2D. So skyrmion texture corresponds to a two-dimensional generalization of winding. So if this is, think of this as a winding as you go from, let's say, left to right and place this, and see how that spin orientation goes around the circle. Then skyrmion topological invariant corresponds to the number of times the two-dimensional texture wraps around the sphere. So if you just at every point place that magnetic moment on a sphere and kind of do it, sort of go around in the continuous fashion and count how many times you wrap around the sphere, that's called Pontryagin index, or skyrmion number. And that number, just like the winding number, is conserved in a sense that if you fix the boundary condition, any smooth distortions of the texture in between will not change that winding number, okay? Or the wrapping number, the skyrmion number, okay? So these are the two examples of topological invariants which are delocalized in real space, okay? So this literally corresponds to some magnetic texture in a one-dimensional Y, and this is magnetic texture in a two-dimensional system. So they delocalize the total integrated density of some underlying, I could define some density of winding and the skyrmion here whose integral is conserved. And that will be the starting point of formulating a hydrodynamic theory. Once that theory is formulated, I'll have to learn how I couple to this hydrodynamic quantity and exhibit the dynamics in experiments. Okay, so that's basically what this talk is about. And the final third example will concern spin glasses. I'll come to that at the very end. Okay, so the spin winding dynamics now is described as follows. So just putting what I said into a little bit of mathematics. The density of the winding, let's define it like this. Okay, some arbitrary normalization factor, but essentially gradient of the phase. You can easily see the corresponding current that complements this density through the continuity equation is given by the local temporal gradient, or the frequency, local frequency of the winding. Okay, so if you fix magnetization at some point, so d phi dt at that point would be 0, you block the flow of this winding dynamic. So if you fix magnetization, let's say at two ends, then there's no flow of winding density in and out, and there will be just reshuffling of this topological winding density in the interior. If you make the ends loose, then you, through the dynamics at the ends, you could inject that winding density and extract it elsewhere and try and build a circuit based on that. Okay? We'll still have to learn how to convert that injection and extraction of topological density at the ends into electrical signals. And you'll see that, surprisingly, it's very easy to accomplish experimentally. All right, so that's the first example. The second example, again, stepping through the same logic, this Kerman density can be written like this. So it exactly counts basically the solid angle subtended by a patch of magnetic texture. Well, that's the solid angle per little area. That's the density, the Kerman density, and that solid angle, like I said, basically the integrated solid angle that describes how many times the texture wraps around the sphere would be conserved. It's conserved because it's a continuous quantity that is discretized. So it's because continuous is discretized, it has to be fixed in time. So that's the whole idea of topological stability. Of course, when I say topological stability, I'm implying that there is some energy barrier that I would have to overcome for this description to break down. And I assume that energy barrier is sufficiently high. So let's just suppose that we're focusing on low energy description. You can ask me later about parasitic processes that kind of kick us out of this description and unwind the textures. So those would be collectively some kind of phase slip effects. Okay, so that is the Kerman density. So n is a unit vector that is a function of x and y and also a function of time. So a dynamic two-dimensional spin texture. J is the appropriate flux. Okay, it doesn't matter, the exact form doesn't matter. It's just I just wanted to put it down just to show that I can actually write it down explicitly. Such that rho and j, again, obey the continuity equation. And just like before, this flux requires dynamics. So if at the boundaries I freeze the magnetic texture, no Kerman density would come in and out. And that is exactly the rephrasing of the fact that the Kerman density, the integrated Kerman density in the interior, subject to the fixed boundary conditions, would be conserved. But more generally, I could allow also the boundaries to have some dynamics, which would correspond to the Kerman density flowing continuously in and out of my system. Okay. All right. This was a video, but because I could not, well, I forgot my adapter for my new Mac. It's just a PDF file. But this is actually an experimental video from my colleagues at UCLA and Argonne National Labs showing a process of generating a gas, an ensemble of Kermans. So think of it as a video with this like spaghetti like magnetic strips being pushed through some constriction by applied electrical current, and on the right a bunch of Kermans come out, and we understand this physics much like this kind of physics of blowing soap bubbles. Again, the details don't really matter. And in fact, the paper itself is quite playful. It doesn't go much beyond of saying that we've realized this kind of physics in a magnetic film. All I want to tell you is that these Kermans are becoming quite tangible objects, even at room temperature. This is room temperature. Actually, the first, I think, room temperature experimental demonstration, direct demonstration of Kerman generation. And there are now many magnetic films as well as bulk materials in which we can control these Kermans in and out of equilibrium. So I'm kind of taking for granted now that not only those winding twists are readily available in magnetic wires as domain walls, but also Kermans are becoming quite readily available, and now can start thinking of more general ways to describe the dynamics and hydrodynamics the way I'm formulating here. Okay. All right. So the general kind of dream is to put this topological hydrodynamics in a circuit. Okay. So again, I'll make some kind of ultimately some computer or architecture in which maybe at the very end I'm going to have some batteries or switches, but the active elements, both the interconnects as well as these guys will be based on insulators. So we're thinking of this topological hydrodynamics as really been responsible for the interconnects, for signals being transmitted efficiently, maybe almost as efficient as superconducting signals or superfluid signals. And for these guys, we're really thinking of it's kind of which both switches and some active elements would be some kind of localized, generally nonlinear elements, and topological solitons like domain walls, skyrmions, come to mind as natural building blocks. All right, but let's not worry about that for now. So let me just say that somewhere here I want to plug in a magnetic insulating wire that will exhibit topological hydrodynamics, and that will play an important role in some kind of circuitry later on. I'll give you a flavor of that in the next few slides. So the next step, I want to learn how to inject this topological flow and how to detect. So we've described it already, right? We have pretty good idea what it is. Now, how do we inject? How do we detect it? How we make use out of it? So let me start with the winding density, which is the simplest one. Okay, what is the winding? Well, the winding, you have to choose an axis around which you wind, and then you wind around that axis, right? The geometry of the winding is very much, basically, it's the same as the geometry of a spinning top, right? You have an axis around which you wind, and sort of the handedness of the winding. So that immediately brings us to this idea. And of course, that's not how we came up with this idea, but somehow that's kind of cool to pitch it like that once you understand everything about it. But let me pretend like, just based on somehow this geometrical analogy, we can anticipate that injecting the winding can be accomplished simply by subjecting the end of this magnetic wire to some excess of spins. Okay, some non-equilibrium density of spin. How do we produce that non-equilibrium density of spins? Okay, we'll discuss in a second, but let's just suppose that I have a bunch of, let's say, let's say those spins are carried by electrons, so this is spin 1/2 particles, and I have excess of them. That excess is called spin accumulation. It's described by a vector mu. The magnitude of that vector is the size of that spin accumulation. The direction is the orientation, so it's pointing out of the plane of the slide. And let me suppose that I'm going to do it in a normal metal. And I'll explain to the next slide. I'll basically do it by a spin Hall effect. This region is an insulator, so I'm interested in topological hydrodynamics in insulators. So electrons cannot flow into this region, but they can scatter off, and as they scatter, they can flip their spin. So that spin flip process is exactly what we need, and this is the spin from out of the plane into the plane of the slide. This spin flip process triggered by the incoming flux of an excess of up electrons is what is necessary to inject, basically to start winding this XY magnet. So in a sense, I'm converting a bunch of spins from the previous slide into the winding, which by symmetries should work. Right? It has the same geometrical structure. And indeed, it works. And we're thinking of it in the following sense. Just like I described, these electrons reflect. Flipping the spin can be quantified in terms of this spin current that flows through that interface. The spin current, again, is polarized in spin space out of the plane, is proportional to the spin accumulation. In equilibrium, spin accumulation is 0. So this is out of equilibrium phenomenon. The prefect, again, for the experts here is the spin mixing conductance of this interface. Now, from the point of view of the magnet, that spin current is a torque, is a transfer of angular, by definition, spin current is a transfer of angular momentum. So that's a torque from the point of view of the magnet. Now, if magnet is moving for some reason at the boundary, so if at the boundary this phase changes, the presence of the torque does work. Okay? So in other words, if the torque is non-zero, it would do, let's say, positive work for one sense of winding, negative work for the other sense of winding. So it creates a certain pumping kind of bias that would wind the magnetic dynamics at this boundary with a well-defined sense of rotation. All right. Again, a side comment to experts, you might ask, well, why do I have to invoke work? I could just describe everything in terms of spin torque, spin conservation, etc. The key is that I don't want to invoke the notion of spin conservation throughout my system. So I have some, I only define spin current at this boundary, but in my magnetic insulator, I may have anisotropies, spin-orbit interactions, etc. The spin, I'm not assuming that spin is conserved. That's why I want to formulate everything energetically, because I don't want to inject spin into this region. I want to inject a topological density, which is robust against things like anisotropies, which would invalidate spin conservation. Okay, in very special case, if the system is axially symmetric around the z-axis coming out of the plane, I could also formulate the same story in terms of spin flow and spin torque, because spin would be a conserved quantity. Generally, spin is not a conserved quantity. The winding is, however, in general, irrespective of energetics or whatever happens with this magnetization to the right, subject, of course, to neglecting phase slip processes. Okay, so that is the bottom line, that spin accumulation, out of equilibrium spin accumulation here in, let's say, a metal, adjacent metal, triggers an injection of the winding density into an easy plane magnet. Now, the rate of this process efficiency, that depends on the details. Of course, if there are strong anisotropies, maybe this magnetization wants to lie along the x direction. So strong anisotropy could pin the phase. You would have to overcome that pinning. So at very low temperature, there would be a threshold for this injection process. At finer temperature, thermal fluctuations allow you to inject this winding, even in linear response. So generally at fine temperature, you don't have threshold for this process. It will always happen, even though it may have to overcome some energy barrier, but there will be some finite rate of this process. And if you have easy access anisotropy on the x-axis, what that winding injection would do, it will simply produce a train of domain walls, chiral domain walls, which will eventually be pushed in and then somehow move around. Once that winding is injected, it has nowhere else to go. It can either come back out at this interface, but like I said, there's some net sense of winding here, so it has to propagate and unwind elsewhere. Okay? So once I start winding, I could detect that winding far sort of down the, down this, along this wire. So I could start building devices in which the signals would propagate over long distances. Okay, like I said, like I promised, okay, let me explain now quickly how that spin accumulation at the boundary could be produced. And that actually goes back historically all the way to Edwin Hall. So already this guy, in some sense, knew, okay, or at least he observed the phenomenon that basically would allow us to inject that spin density, namely the anomalous Hall effect, or a slightly more modern version of that, which is the spin Hall effect, that precisely allows us to accomplish what we need, namely sending electrical current in any material, let's say in this direction, produces a flux of spins up to the right and spins down to the left, so long as you have some spin-orbit interaction in the material, not assuming anything else, special symmetries, nothing. Every material has this effect. Typically, the heavier the material, the larger the effect. So it's much larger in platinum, much weaker in copper and aluminum, simply because spin-orbit interactions scale with some power of the mass of the atoms that make up the material. All right. So meaning that if you take a slab of any conducting material, send electrical current, this edge of this film will act as a spin injector. And you could connect this edge now to your XY magnet and push winding into your XY magnet. So the spin Hall effect is the practical injection mechanism that couples electrical current to the winding dynamics. Okay, the reciprocal of that is the inverse spin Hall effect. So of course, we always have on-Zaga reciprocity. So if electrical current can inject winding, we can expect that we can detect this winding down the stream by detecting electrical current through the inverse pinhole effect. Okay, that's kind of illustrated here. So another metal down the stream will absorb the spin current and convert the spin current into measurable voltage. Okay. Now that has already been experimentally accomplished, albeit not in the regime of the topological hydrodynamics, more like in the regime of magnon diffusion in magnetic insulators, somehow like more mundane, but still spectacular. So the first experimental demonstrations of kind of putting all this physics together, namely using one platinum contact to inject spin into an insulator. Now this the spin is simply converted from electron spin into the spin carried by magnets, and the magnets diffuse and can be detected in another platinum contact over very long distances, not infinite because the magnets decay, unlike my topological hydrodynamics, which basically does not decay, or at least much more protected. The magnets will eventually decay, so there is some diffusion length, but over sufficiently large distances, you could actually measure such signals in a good material, such as yttrium iron garnet, magnetic insulating ferromagnet. An experiment in Holland. There was an experiment here at UC Riverside in which same physics was utilized. The geometry was different, was a layered system, basically exactly illustrating the same physics. This is just cartoons, theoretical cartoons from the experimental papers. And that's the physics at the interfaces that's responsible for injecting spin hole induced spin current into magnetic insulator and then converting it with a, well, ultimately via the inverse spin hole effect into measurable electrical current. So all the tools, experimental tools are in place. Now all I want to do is replace this diffusive medium of magnets with the topological winding dynamics. Okay? Of course, you could convert one spin into another and propagate it. I want to convert spin into winding dynamics and study the winding hydrodynamics. So that was our proposal a couple, 3 years ago or so. Again, that's the illustration of what I already described by putting everything together. So I have an XY magnet. Any XY order parameter, some easy plane ferro, antiferromagnet, or some kind of planar spiral helical order would be a good good candidate material, insulating. And then I connect on the two sides this hydrodynamic, my topological hydrodynamic medium to metals, apply electrical current here to inject spin, and then detect the winding that comes out here by measuring voltage in this second metal contact. So it's exactly the same geometry as in the experiments that I showed before. Essentially, this similar geometry, but the medium is different. And I'm not supposing that the spin is even conserved in this medium. Namely, the spin accumulation here is converted into winding. That winding propagates, and then as you unwind at the right end, the spin current of this interface comes out proportional to the frequency of this unwinding dynamics. This is called spin pumping. And via the inverse pinhole effect, that produces the measurable voltage. In fact, if you put all the signs together correctly, you would expect this process to mediate a kind of, hydrodynamics to mediate a kind of negative drag between this metal wires. So electrical current injected here far down the stream would produce a bias which drives electrical current flowing in the opposite direction. Of course, in the open geometry, we just measure voltage. In the closed geometry, we would measure electrical current flowing in the opposite direction. So it's a kind of drag effect. That you could quantify it as a drag effect. And you could ask, well, what is the drag coefficient between these two sides, and calculate it. That's what we did in one of these papers. All right, so and then you could start building up into more complicated circuits. But I just wanted to get a couple points across. So first, again, one of these guys is the same, basically is the same setup as before, But now let me apply electrical current to both contacts. And let me apply electrical current in the antisymmetric fashion or symmetric fashion, just to separate dynamics from the texture. So in general, when you say inject this winding from a left side, like I said, there's some winding and it propagates. So at any given time, there is both texture, spatial texture, and dynamics. And in these two circuits, we can actually separate the texture from the dynamics. In this configuration, we would have, when electrical current is circulating around my magnetic film, we only expect to have dynamics without spatial texture in the steady state. And you could actually calculate, so putting this spin Hall, inverse spin Hall physics together, you can show that in this configuration, the resistivity of these metallic wires would seem kind of lower in the presence of this medium in between. So in some sense, this magnetic dynamics lubricates the flow of electrons that go around this magnetic region. The resistance is higher in this configuration when the currents flow parallel to each other. And like I said, these two cases separate the dynamics from the texture. In this case, we have just the dynamics. In this case, we have just the texture. So in a sense, we are injecting spin current here. We're draining spin current here. So in the steady state, we simply have a static spiral with this injected and drained spin current being basically proportional to the gradient of the phase in between. And you would really not measure anything when the dust settles. This magnetic texture is static. So from the point of view of this metallic wires, you basically see no dynamics. So the metals would not pick up any kind of electromotive force from this magnetic dynamics unless you have phase slips. Okay, and you will have phase slips. So in general, this magnetic texture, it's a metastable state that tries to unwind. It's a state that costs finite energy. So the system will try to find a way to unwind. And that happens through phase slips. Okay, basically, at some point, you will start creating vortices, anti-vortices into the in 1D. Magnetization ultimately by thermal fluctuations will come out of plane, cross over the north or south pole, and ultimately unwind, either by thermal fluctuations or by quantum fluctuations, so thermal or quantum phase slips. So this is a phenomenon which is familiar to people working on low-dimensional superconductors and superfluids, in which dissipation is dominated by such phase slips. Because superconducting superfluids, there are, the transport is also relying on topology, and that topology is unwinding the winding number associated with topology. The phase slips are detrimental to it. But now for us, it's kind of cool. Okay, in a sense, the phase slips are detrimental, but in this geometry, we can measure those phase slips directly. So as the phase slips happen somewhere in the interior, they are manifested now from the point of view of this metal contacts via some steady state unwinding taking place at the boundaries, right? Because the system wants to maintain a certain, in the steady state, certain kind of winding, and then when spontaneously by thermal fluctuations the interior is being unwound, then the boundaries have to be rewound. And if you work everything together, that in a steady state, that rewinding in the boundaries is directly measurable as a shift of your voltage, or the shift for a given current, or the shift of your resistance. So we can measure those phase slips directly through the magnetoresistance. We can go to zero temperature and by the same token measure quantum phase slips. And in this two-dimensional film, that allows us to study, for example, Kostelis-Taulas physics. The physics of the phase slips is exactly like Kostelis-Taulas physics in superfluid films or superconducting films. So again, I'm kind of just giving you flavors of extending towards some interesting phenomena. Some of that starts just proceeding by analogy to the superfluidity, but that analogy very quickly breaks down when we're starting to appreciate the aspects which are unique to the magnetic systems and which are absent from the superfluid films. And that happens very quickly. So this is an example of that. So then a couple years ago, we thought, okay, let's, instead of easy plane magnet, which is something a bit less generic and more delicate, let's start with a more generic situation of easy axis magnet and create a superfluid or establish a superfluid, this kind of winding, spin superfluid winding dynamics along the domain wall. So if magnetization goes from, let's say, up to down, the easy axis is out of the plane, so some, again, two-dimensional, three-dimensional material, the domain wall is a contour along which magnetization lies precisely in plane, right? There's a contour. Let's define domain wall as a contour along which magnetization out of plane is 0. Okay. So along this contour, now you have again easy plane, easy XY type of system with which is one-dimensional in space. Okay, but this texture, one-dimensional texture, again, is free to accept or reject some winding dynamics at the boundary. So now, again, we can play the usual tricks. We can apply some spin hole bias and measure the propagation of winding by these non-local signals, like I described before. But now, okay, that's good. Now you will ask, well, what about phase slips? Yeah, so we studied phase slips for a while. We understand phase slips has been really crucial as limiting this superfluid aspects in one-dimensional systems. That's, of course, well understood in superconductors. That's it was a big deal for one-dimensional superconductors. People still write papers about that. But now you realize in this magnetic system, you cannot really create a phase slip because we defined this domain wall as a contour along which the out-of-plane magnetization is 0. To accomplish phase slip, magnetization has to come out of plane and cross through the north pole or the south pole. And according to our definition, that is not geometrically allowed for a domain wall. So naively you think, okay, there's just no phase slip possible at all. So even though the system is one-dimensional, the supercurrent would be perfect. However, that is assuming that this object is one-dimensional and doesn't cross on itself. The moment you allow some kind of loop to be formed and this guy to cross on itself, that opens a channel for the phase slip, because basically when you cross, to define some net winding, you have to go along some one-dimensional contour. If that one-dimensional contour crosses on itself, you can no longer define the winding. So there are two ways in which the winding cannot be defined. Either the magnetization comes out of plane, crosses the north pole or south pole, so then the azimuthal angle is well defined, or the contour closes on itself. And it's really the latter that happens here. And amusingly, when that contour closes, and as illustrated here, it's a three-step process, A, B, C, so you wound, there's some trivial winding, then you can smoothly unwind that by creating a loop into this kind of trivial state, but necessarily that process spits out a skyrmion. So now in this geometry, we connected this winding dynamics to the hydrodynamics, to the skyrmion hydrodynamics. So the bottom line now is that biasing this kind of one-dimensional domain walls and creating the winding and simply waiting for that winding to relax produces a transverse flux of skyrmions. Okay, so this is some kind of interconversion of longitudinal flow of winding to the transverse flow of skyrmions, and vice versa. If we produce skyrmions by some other means, we can use this domain wall to kind of trap those skyrmions and convert the flux of skyrmions into some measurable voltage on the side. So it's a kind of converter of one type of hydrodynamics to another. Now that brings us to the question, well, what about skyrmions in their own right? So we understood the winding hydrodynamics, the skyrmion hydrodynamics. We understood that winding could be injected and detected directly. So that's just one example. Can we do the same for skyrmions? Can we inject and detect skyrmions directly? Without using this complicated intermediate step like on the previous slide? And the answer is yes. And that is it turns out to be also very simple. So the first thing that comes to mind, okay, so now we're playing the same game. We have now two-dimensional magnetic material with a skyrmion. So I'm showing like a half skyrmion, a maron. And I'm asking, well, is there some simple way to inject the skyrmion by messing around with my normal metal? If you put a spin accumulation here on the side, you can easily show that that does not really work. So the previous trick is not going to do anything. The spin accumulation tries to wind the texture on the right. There's no tendency, also by symmetry, there's no like somehow geometric compatibility with injection of skyrmionics. Instead, what happens is something even simpler. So something that is known as adiabatic spin transfer torque. So basically, if you're sending, as before, electrical current tangentially, but turning off spin orbit interactions, so not invoking spin orbit interaction, that tangential electrical current will couple to the magnetic texture exposed at this interface in the following way. The torque produced by the electrical current onto the magnetic texture will look like this. So it's going to be proportional to the electrical current times derivative of the magnetic texture along the direction of the currents, along the y direction. And it turns out, if you calculate work associated with this torque, now this torque is something very well established, very well understood to the people in the field of spintronics. If you calculate work due to this torque associated with some general magnetic dynamics now along this one-dimensional boundary, that work ends up to be, just plugging this into this expression, n cross at the n is just three-dimensional differential of the angle. It's just basically it's just a rotation angle, right? So the work is given by the torque times the incremental angle. That is given by this integrand, the corresponding the integrand that you pull out after substituting this torque here boils down simply to the scalar triple product of z, the normal, the electrical current tangential flowing over here at the boundary, and the skyrmion flux at the boundary. The skyrmion flux that I defined on one of the previous slides. Okay? So again, in the presence of electrical current of a given sign, there is an energetic tendency for the skyrmion flux to enter the system. And again, it will enter, if nothing else, through some thermal fluctuations. Right? Now, it doesn't have to be lumped into some kind of skyrmions. You do it even next to some two-dimensional Heisenberg ferromagnet. That skyrmion density will still be injected through, if nothing else, through some continuous fluctuation that carries a skyrmion density. And then you could even start asking questions, well, like what kind of drag effect, long-range drag effect, would the simple Heisenberg ferromagnet or antiferromagnet mediate through this kind of physics? Yeah.
What's this coefficient?
This is polarized. Okay, so everything else is clear. P is the spin polarization of electrons which move past along this interface. So physically, that stems from some exchange interaction, some proximity effect. So these electrons have, of course, to experience magnetism through proximity-induced exchange, and that P basically parameterizes the strength of that exchange. Because in the absence of exchange, electrons don't know about texture, get nothing, and the stronger the exchange, the better the efficiency. So that's very cool, and of course, reciprocally, that means the skyrmions, if elsewhere, if they get ejected through some other interface, that ejection will generate electromotive force, a measurable electromotive force, just by the Onzaga reciprocal of this physics. Okay, so and again, the philosophy is just like before. You have a medium, you apply a current that pushes skyrmion density, and that skyrmion density is completely conserved once it is in the medium, and it has to exit the system through one of the boundaries, and that's just the usual hydrodynamics. You push something in, and then you detect it somewhere else down the stream. Of course, okay. So the structure in which we can detect the flow of skyrmions, injection and detection, is similar to before, except that now we're using spin transfer torque instead of the spin Hall effect. Again, there's this insulating film contacted by metals, which we can bias in different ways and generate different types of flows of skyrmions. We can also use it. We can, like I was saying on one of the introductory slides, we can try to use this transport measurements as probes of the state of the material. So, for example, the films, we could take a film that, as a function of some Jalshinsky-Maria interaction and isotropy, such that as a function of magnetic field, there's some phase transitions between magnetic state, skyrmion crystals, some helical order, and by measuring the drag effect in this geometry, we can look at the signatures. We can look at the signatures of the phase transitions through the electrical drag, so electrical signatures. And again, we can utilize that physics for devices. Okay, and just one last remark. Not so maybe interesting for the general audience, but for people in spintronics. So this is kind of the last idea that we come up with that hopefully might become useful, that generalizes this notion of topological hydrodynamics to spin glasses. Now this could be simply some magnetic material that is amorphous, frustrated, completely globally disordered, but locally forming some kind of correlated spin textures. And we can use the same trick of applying, again, back to the spin Hall effect, applying spin accumulation and using spin accumulation to trigger winding dynamics. Now, that winding dynamics doesn't have to lie in the easy plane. In fact, now we can inject spin oriented arbitrarily, and in a spin glass, the spin glass will naturally wind in the plane perpendicular to the spin injection. Before, if I start with an XY magnet, I would have to inject spin by spin Hall effect perpendicular to the easy plane. For a spin glass, I can inject spin arbitrarily, and the spin glass can still accommodate the spin injection via this kind of, this sort of like SU2 kind of winding that is now readjustable according to the direction of the spin accumulation. Okay, so the same physics applies. So our suggestion now is to look for strong non-local signals through disordered amorphous materials. And incredibly, at the same time as we were thinking about it, an experimental paper came out. I'm not sure at this point whether this is directly related or not, but there is an experimental paper that claims exactly this sort of thing. Maybe the origin of this is different, but something that needs to be understood. Long distance spin transport. Again, the injection detection via the spin Hall effect through a disordered granular disordered magnetic insulator. And they actually also invoke the notion of spin glass as a speculation. And it's kind of interesting to see whether this goes anywhere, develops anywhere. But okay.
Spin glasses the classic ones are metallic, right?
So you say the classic?
The classics, the old ones.
Like the materials?
Metallic, like copper, manganese.
Okay, so.
Okay,
so first of all, I'm not an expert. It's something that I'm trying to learn about. So we don't want to have conductivity. Yeah, we really want to study these things in insulators. Of course, conductivity is completely unrelated issue. Like it's just there, right? You say in practical materials, it just happens to be there. Well.
So this would be an insulating.
At least I'm not sure if, by the way, let's say in this experiment. It's simply a granular version of a material that is known to be a ferromagnet. And they say maybe it's a spin glass or some kind of glassy state. I mean, all I need is material to be random and locally to form some kind of correlated spin arrangement. Okay. Again, depending on whether it's really in the glassy phase or simply some kind of amorphous phase with some correlation length may affect the details of how our signals would scale with the distance. That's something that we need to study. If it's metallic, because you measure drag, if it's metallic, of course, there are parasitic contribution to the drag that you have to eliminate. Fortunately, so it's just an extra headache, but it's not fundamentally problematic because you could eliminate the drag simply geometrically. If the length of this strip is much longer than the width, that metallic contribution to the drag would be exponentially small. Yeah, it's a big headache to deal with, but
About frustration, that's another important component.
Yeah, so of course this is all based on frustration.
Separate from disorder.
Frustration, you mean of course, I mean the spin glasses are frustrated, but you mean like ordered frustrated? Yeah. So again, of course, you could think about many different things, but coming from this angle, what we're interested in is identifying topological, any kind of topological quantity that is extended through the system, like the winding number. So, again, if it's a frustrated system, okay, does it order? Is there, are there some topological solitons, some excitations to which I can assign some topological number? So, basically, I don't know. So we're definitely trying to. So we're trying to think of different examples. These are the 3 examples that we know of now. But the notion is very general, and we're trying to somehow generate more examples. But this is exactly the kind of things we're thinking about. Let's just start with some more exotic material. But our guiding philosophy is, and let's look for topological excitations. And then how do we couple those topological excitations? Okay, that's kind of the next thing. So first we develop hydrodynamic description, and then we need to be able to couple to them. Okay. Well, that brings me to the end of my talk. And thank you for your attention. Also, thank the people that support us, the agencies. Thank you. Yeah. So, okay, thank you for asking, so we can talk more about this. What is spin glass, right? Let's just imagine a completely random spin. Let's just imagine some amorphous material with, let's say, a random exchange interaction. So there's no simple ground state, but when the system equilibrates, there's no long-range order whatsoever. There's no magnetic order. Okay, everywhere at each point the orientation is random, but it's frozen. That's the key. So the spin orientation is random, but locally frozen. Just like amorphous material like a glass. There's no crystal order. But it's not a fluid, at least not on any reasonable time scales, because locally everything is frozen. So each local spin in the presence of its neighbors has some clear preferred orientation. Okay, and all other spins nearby also have preferred orientation. So that means that at any given point, the system is frozen in a certain state, and its low energy excitations are kind of like phonons in a glass. Namely, locally you cannot move this guy, but all of these spins, so long as there's still global SU2 symmetry, or approximately, there's a global SU2 symmetry. Okay, so if you have a chunk of the material, globally you could move all the spins. Okay, so now if you apply some spin accumulation at the boundary of this material, the spin accumulation, all it does is it tries to, you have this kind of energetic tendency for the spin accumulation to twist your global arrangement around the direction of the spin accumulation. And that propagates basically as a superfluid, like before. So this kind of twist, they are responsible for phonon-like gapless excitations in spin glasses. And those are, at low frequencies, those are the building blocks for our topological hydrodynamics. Okay, so it's really that, think of it as kind of coarse-grained global reorientation of this kind of arrangement, which is different from paramagnet. Paramagnet, like at each point, you have basically on average zero spin. In a spin glass, it's kind of average over some finite patch. But at each point, it's finite, just points randomly. So it's like, I think of it as like SU2 superfluidity. Like normal superfluidity is U1. This one is SU2 because the order parameter is like a rigid object. It's parameterized by 3 Euler angles rather than 1 Euler angle. That's why it's more versatile, it is conceptually, and because now you can inject spin along arbitrary orientation that still will propagate collectively through this kind of rigid type of reorientational dynamics.
Yeah. So basically what you're saying, instead of moving spins, we have to move these topological excitations which conserve.
Yeah.
How good is this conservation number and what it depends on?
Okay, so exactly. So this is another direction of research, right? So in it's the same as kind of question of what, go back in the day, like what is the conductivity of a one-dimensional superconducting wire or two-dimensional superconducting film, right? So we understand that conductivity has been, normal conductivity has been determined by phase slips, okay? So that's, at least that's a starting point. So in a one-dimensional, if you have a one-dimensional XY magnet that transmits this one-dimensional superfluid, the physics of the phase slips would be very similar. Also two-dimensional would be very similar to phase slips in superconductors. So there's basically an energy barrier. So if it's a one-dimensional case at finite temperatures, it's quite simple. There is an energy barrier for the phase slip. So there's some easy plane anisotropy. And the phase slip is accomplished by magnetization coming out of the plane and crossing a north or south pole. So it creates basically a finite-sized solitonic object that has an energy. You could calculate what that energy is. It's basically determined by something like square root of stiffness, rigidity times the out-of-plane anisotropy. And then the phase slip rate would be thermally activated. So the parasitic normal dissipation would be proportional to E to the power minus this energy over kBt at finite temperature. At zero temperature, it doesn't freeze out completely. There is some remnant quantum phase slips. And this physics could be mapped onto what people already know in superconductors. So we've done that. So we have a paper on thermal phase slips, quantum phase slips, and you could basically proceed by mapping, do much by mapping superconductors. And
what it was actually solving, is there some sort of understanding that the bigger these solitons are, or whatever, skyrmions, the bigger this energy of the phase slip or whatever? Is there some simple rule that tells you in some regime this will be totally unexistent and they can do it?
Right. I mean, yeah. So basically, yeah. I mean, we can. It's clear what needs to be somehow, theoretically at least, it's clear what needs to be improved. So, but basically, we just have to. So let's say if it's the winding dynamics, then the larger the easy plane anisotropy, the better, right? And we can estimate the appropriate energy scales, etc. For skyrmions, skyrmions would seem more robust. Because so long as the skyrmionic texture is continuous, there's no way to unwind them. So to unwind skyrmions, you have to go down to the atomistic scale. Okay, so then the energy that protects skyrmions is determined simply by the atomistic exchange. But of course, there are some spots in which atomistic exchange, there could be some impurity, it could be reduced. So, this process, of course, the details and could be very complicated in the different regimes of it. But, okay, we studied these things in some very simple limits. But one useful statement to say is that we can actually, that's kind of one of the points I was trying to make. So apart from trying to calculate these things, we have a way to measure this phase slip rate, this kind of parasitic unwinding rates directly. Just by kind of separating dynamics from the texture. And when the texture is in place, we can simply measure directly the dynamics entirely due to unwinding. So that's kind of, that's sort of cool. And then if you start asking about the phase slips for the spin glass, we have no idea how to think of this unwinding in a spin glass. It's kind of like if you take a rod and you twist it very hard. If you wait for a long, long time, somehow that twist, somehow it will untwist somehow, right? Because the twisted state, the twist, and you clutch the ends. Of course, it has to somehow untwist, over, I don't know, millennia or whatever, right? Okay, this system may happen much faster, but what is the physics of that untwisting? It's very complex. It has probably to do with some dynamics of dislocations, etc. So really understanding even just the energy scale that determines the rate of phase slips in spin glasses is kind of a complex problem. And maybe we're not the people to make progress. Maybe there are better experts on it. But the main message I'm making, trying to convey at this point, is that we're suggesting to experimentally at least start looking for these things. Okay, yeah. So of course, this is another important issue. There are two types of dissipation in the system. phase slip, but there's something that I completely shoved under the rug. Anytime you have dynamics in this system, there is dissipation because the environment knows about this dynamics. So in this magnetic systems, typically at low frequencies, that's Gilbert damping. So there's always dissipation that's proportional to some material-dependent parameter times the local frequency of this dynamics kind of integrated over. So the moment actually you have kind of a steady state process and the system is doing something useful, there will be dissipation. You know, static configurations do not dissipate, only the phase slips. And so if you do some, some manipulations quickly, there will be some dissipation due to phase slip and some dissipation due to some kind of transient dynamic. So the system, there's always dissipation, but even in the presence of the dissipation, the signals, because of the topological stability, the signals that propagate through the system, like this drag effects, are algebraic in the sizes, not exponential in case of diffusive process in which instead of creating this winding, you create just kind of localized spin excitations which propagate, and the spin excitation can simply disappear. Right? Like in your experiments, as you know, the process is diffusive, so there is some diffusion length over which the signal, beyond which the signals decay exponentially. In our case, even in the presence of damping, the signals are algebraically long-ranged. And okay, the damping is just a practical matter in the end. We can estimate for which sizes damping becomes important, for which sizes it's not so important. But it is an important practical matter, not so fundamentally of a concern. So far, it's all classical, right? But yeah, but okay, there's so here I'm describing everything in terms of some like really coherent dynamics. I mean, so far I have not formulated like any issues that somehow would suffer. None of this would somehow suffer from dephasing. There's no sense in which in any of this. For example, if you do a ferromagnetic resonance, right, and you have some kind of inhomogeneous broadening, right? So let's say dephasing due to inhomogeneous broadening, that would broaden line widths. Here, this plays no role. So you have some inhomogeneities, disorder. So if you do some kind of local measurement, you would measure dephasing. But this winding business is just so robust. Here there's no sense of dephasing. But the only context, at least, I have not come across any situation in which we worry about dephasing, unless we start thinking about some quantum regimes in which we want to build some kind of a quantum device. Like you can naturally try to build some kind of quantum devices in analogy to the superconducting qubits. So we have a proposal for some spin superfluid qubit operated by the spin Hall effect. And then, the issue of dephasing comes up. But not in this sense of my talk today.
So you're assuming that you don't have time-dependent fluctuations?
No. It's just they don't. It's not that I'm assuming that. I'm just saying that the behavior is kind of robust against it. I don't know in which, like I said, you could add fluctuations, you could add some noise in the system, inhomogeneities. That doesn't really change much. Just like in a superconductor, a superconductor just is so robust somehow. I mean, you inject at the boundary, you wind. That winding, that noise could create some kind of fluctuations of your density, but it's conserved. It cannot unwind just by local fluctations.
You're assuming static disorder, right?
Static, dynamic.
Because dynamic disorder could lead to dephasing.
But dephasing of what? So basically, I simply don't, we don't encounter any issues of dephasing, at least in the context of these topics. So let me just say, naively, I just say this kind of behavior is robust. This kind of low-frequency hydrodynamics and all these experimental consequences that I discussed, they're just robust against small random fluctuations. Maybe.